I'm Nigel Springett. I'm going to introduce to you today our new clipper. I don't know if you've heard about the clipper, but it's a completely new type of measurement device. It allows us to measure the current in MOSFETs without needing to break the current loop or to insert a current probe. It also, because if we know the current, we can actually estimate the junction temperature on the basis of the increasing RDS on as the device gets hot. What I'm going to do today is show you the application of the clipper in a typical PFC circuit. I have here a TI demo board. It's for the TI UCC 3817. We have the input, the power inductor, the MOSFET switching transistor, a silicon carbide diode on the output, and then the 400 volt output. We've connected this up on our lab with a DC source to make measurements easier and a simple load. The clipper comes in an aluminium protection case, transport case, with various accessories. In the middle, of course, we have the clipper, which is rated up to 1700 volts. Then we have various BNC to SMA adapters. This is a male one. We have a female BNC to SMA adapter, and some polarity changes for the clipper, two of those, and some SMA boxes, sockets to screw on, to solder on onto the unit under test. To use the clipper, it's very, very simple. You can take the standard clipper, which has two ranges, a low voltage range and a high voltage range with this little switch. We can add the adapter, the first adapter, just screw it on, make sure that the parts line up and it's tight, and then we can screw the whole adapter on to the clipper. We don't need to use any special tools or anything. This can all be just done hand tight. And then finally, very important, the output of the clipper, although it's a BNC box, if we use a BNC 50 ohm cable, we'll have problems. The measurements will be too slow. So we're using a typical 10:1 scope probe with a BNC to scope probe adapter on the end. And we plug that into the output of the clipper. And basically, now we're ready to take the measurements. So now we have the full setup, the test setup. We have the 10:1 scope probe with the BNC to scope probe adapter, and then we have the clipper. The clipper has no galvanic isolation, so of course the voltage on the output can be dangerous. It's also worth mentioning that the clipper has a plastic case. This is to prevent short circuits in case we actually put the clipper on top of the PCB. Other things about the test setup worth mentioning are that the SMA cable distance, or the distance from the distance between the device under test and the SMA cable should be kept very small. We've got a distance here of about 5 centimeters. This is close to the maximum that's good for high-speed measurements. We are looking at a voltage of about 1 volt across the MOSFET when it's conducting, sometimes less. And so any inductance here will cause common mode currents which will upset our measurements. The clipper is not polarity protected. This means the inside for the clipper is the positive voltage, and the outside, the ground, is the null volts. So if we're connecting to a MOSFET, the inside must be connected to the drain of the MOSFET, and the outside, the black wire here, is connected to the case of the clipper, which is the source of the MOSFET. To enable or give us a reference that most people understand, I've connected a differential probe again across the MOSFET. So across the MOSFET we have the clipper looking at the drain source voltage, and we also have a differential probe which will be showing us the whole drain source voltage. On the display on the oscilloscope, I've connected the differential probe to channel 1. Channel 1 is at a setting of 100 volts per division, the yellow channel. And channel 2, the blue channel, is at 200 millivolts per division. So we can see we have a factor of 500 to 1 between the two channels in resolution. I turn on the PFC. We have quite a low load here. We're a load of about 100 milliamps. We can see the blue channel, which is representing the voltage across the MOSFET when it's turned on, starting at close to 0 and then linearly rising as we would expect because of the voltage across the inductor and the current in the inductor building up. You can also see it's stable, and on the yellow we can see the whole voltage across the MOSFET to 400 volts peak to peak. If I increase the load, we say the same sort of thing. The yellow, the whole drain source voltage stays constant, but look at the blue voltage while I'm talking. This is the voltage across the MOSFET when it's conducting, and you see it just slowly increasing as the MOSFET heats up. But I can also show you, or we can also look at the time, how quickly this blue voltage actually starts to be useful. So after maybe 200 nanoseconds, we're getting a very good indication of the voltage across the MOSFET while it's conducting. And of course we can use this now for many things to tell us how hot the MOSFET is, if we know the current switching, or we can use it to give us an idea of the current that's flowing. What I'm showing now is the typical way we'd measure the current in a circuit, which is using the standard Tech current probe or LaCroix or somebody's. But the big pain is we have to cut the tracks. So in this case we've cut the tracks, we've inserted the big loop, which of course increases the voltage across the MOSFET. And on this board I had to cut the tracks on both sides of the PCB. It's quite difficult, as we all know. So of course using the clipper we get a good representation of the current. But what I want to show you now, when we look at the scope, is that the relationship between the measured current, the green trace, that's on 500 milliamps per division, and the blue trace, which is of course the voltage across the clipper. And the red trace here, this is the maths. We're using the scope to do the maths to calculate the actual dynamic on resistance of the MOSFET during conduction. This is something which, as far as I know, only the clipper can do for you. So we can measure the MOSFET on resistance while we're switching. You can see with the yellow trace the whole drain source voltage, 380 volts. So we're switching a current here of about 500 milliamps peak, and we can see an RDS on from the MOSFET. It's actually increased now while I've been talking. It's about 380 milliohms. This coincides with the data sheet values. If I increase the current, make the MOSFET do some work, again we see the voltage across the MOSFET during the conduction phase increasing, and we can also see now with the red, the mass channel, the RDS on of the MOSFET increasing as it heats up. So the current is staying constant, but we're seeing the blue voltage, the resistance of the MOSFET increasing. So we're now gone up to nearly 520 milliohms because the device is getting hot. If I reduce the current, we can see the RDS on stays constant. It's still 520 milliohms, although we've got the lower current, and now because the MOSFET is cooling down, the current is, we see the RDS on reducing again. So what we can really do now is test how good our thermal performance is of the heatsink and the insulation, everything. We really know or can estimate the junction temperature of the MOSFET if we want to cut the tracks on the PCB. Or we can just use the clipper for comparisons and production testing and everything to ensure that the thermal resistance, the thermal cooling network is working properly. Again, we have the PFC demo board with the current clamp. and the differential probe measuring the drain source voltage. But what I've done this time is I'm using a differential probe. I'm using it on the times 20 range to give us a bit of galvanic isolation, a bit of safety. So really, of course, everything after here is safe. We're not guaranteed, we're not necessarily connected to ground. And what we can see on the scope again is the red trace, which is the maths. The blue trace is the voltage across the clipper. And the yellow trace is the whole drain source voltage across the MOSFET, with green being the current. So the first thing we can see here is that the blue trace is actually going negative. So there's a small problem with the differential probe. It's not actually doing a great job here. A bit of noise or something going on here. And it's giving us a slightly too low RDS on from the MOSFET. So we're having a MOSFET RDS on of about 330 milliohms, but we're still measuring at quite low currents. So a peak current here of about 700 milliamps. If we go up to the point where we really want to start measuring stuff, where the voltage across the MOSFET gets bigger, then of course the offset caused by the differential probe becomes less significant. And again, we start measuring almost immediately the 440 milliohms RDS on for the MOSFET, and we can see the same waveforms. They're more noisy because of the attenuation of the differential probe. And we can see it slowly increasing, the RDS on just slowly creeping up 500 milliohms already. So if you don't want to use a times 10 probe, where you want a bit more safety, a bit more isolation, one thing is to use a standard differential probe with the clipper. The last thing I'd like to show you in this demonstration is how we can use the clipper to actually measure the forward voltage across a diode. Now you might think that you don't really need to measure this, as in the data sheets, but the new technology diodes, for instance silicon carbide or the GaN trunk diodes, which will be coming out soon, they have a forward voltage which is very, very much dependent upon junction temperature. So the higher the junction temperature, like the MOSFET, the higher the forward voltage. So by checking on the forward voltage, we can again estimate what the junction temperature is. So what I've done here is we've put the clipper across the silicon carbide diode in this power supply. We're using a 3 amp Infineon part. The clipper's on the 2 volt range, and because this voltage is now the diode is jumping up and down at 400 volts, I'm using an isolated oscilloscope here. So I'm going to turn on the PFC, first of all at very low current, and we can see the voltage across the diode. We're just using channel 1 here, and it's at 500 millivolts per division. So we're seeing actually it's about 1.5 volts at peak current, and then falling to about 1.2 volts at the lower current before the current drops to 0 and the diode turns off. If I lower the current a bit, we can then see how the diode stops conducting, or the duty cycle reduces on the diode. So increase the current, and we can now see the forward voltage increasing. We now have a current of about 2 amps. So we can see now this is a 3 amp diode. We've got about 1.75 volts across the diode. And if I increase the current more, we might even see the start of a small thermal runaway as the device gets hot. Probably not yet. We're not running at high enough current.